Okay, everybody, we're going to go over the nuclear radiation and the half-life today. In order to do so, we need to first quickly review what we were talking about last time. So last time we were talking about the idea that sometimes waves act like particles. So Max Planck's theory was, or part of it was, that the energy here of a photon or of a particle of light is equal to Planck's constant, h, times frequency, f, so hf. And Planck's constant can be given as two different values, right? They're both found in your IB data booklet. There's one in terms of eV seconds, so EVs is the unit of energy, and there's one in terms of joule seconds, right? Also in another unit of energy, depending on which one you're talking about. Okay, we also last time talked about wavicles and just the fact that it's not an official term. It's just something I've been I call, and other physicists also use that term as well. I don't know if it's an official term. Just the idea that particles can act like waves. Waves can also act like particles. As part of that, de Broglie said that we're going to imagine the electron, instead of orbiting around the nucleus, it's going to be a standing wave that just kind of waves around it. Okay, and so as a result of what he said, we got Bohr's model, which is this idea that there are specific energy levels, because since there are only certain standing waves that will fit, right? There are only certain energy levels also that the electron can have. Okay, so then the last thing we talked about was also that this idea of an electron volt, which is a unit of energy, which we mentioned earlier, right? And the electron volt was defined as the amount of energy that comes from one electron moving across a potential difference of 1 volt. The main thing that you know how to convert EVs into joules, and that is right here. Okay, so 1 EV is equal to 1.6 times 10 to the negative 19th joules. They do not give you this equation on your IB data booklet, but they do give you this number, 1.6 times 10 to the negative 19th. However, it's kind of disguised. It is the charge of an electron, or elementary charge. That's where that number is listed. So you have to remember that when you're converting from EVs to joules, you need to remember that the conversion constant is simply the elementary charge. It's kind of a little bit easy to remember that if you remember the name of EV, which is electron volt, right? So the electron there kind of gives you a hint of what the number is, and hopefully you'll remember on the test. Okay, so the things that we never got to was this idea of, okay, what do we do with this information? Okay, so because electrons can jump from different shells, so you can go from a low energy level, right, from a low energy level, and then you could jump up to a higher energy level. How do you get up to those different energy levels? Well, as we've shown before, the electron can be a photon, which is just energy, wave, right? And it can come in and it can be absorbed, and that electron can jump up to a higher energy level. And then when it falls down back to the lower energy level, it can emit the photon back out, or a photon. So over here we have a graph of what the energy levels might be, right? So for ground state, that's the lowest state. It's negative 5 EVs, so energy is in EVs. Negative 5 EVs of energy in this random example. Perhaps the next highest energy level that the electron can be at is negative 3.5 EVs. And then the next highest one would be negative 1 EV. Right, and then the next one, negative 5, etc., and it keeps on going up higher and higher. So if you had an atom with an electron at the ground state right here, and you sent a photon at that atom with the energy of 1.5 electron volts of energy, right? That would be enough energy to, wait, is that right? 1.5? Yeah, 1.5 EVs of energy. That would be enough energy to bump up that electron to the first excited state. And it would sit up there and eventually it would fall back down and then emit that photon back out, and that photon would have, again, 1.5 EVs of energy because it would drop back down. Okay, or if it's at the ground state and you shoot a photon at it with 4 EVs of energy, it might jump up to the second excited state, right? So depending on which standing waves can fit on there. It depends on what the energy levels or the energy shells of an electron can have. So here's a typical question, might be something like, what is the frequency, the photon, well, that doesn't make sense. So what is the frequency necessary for a photon to have in order to excite an electron from the ground state to the third excited state? Okay, so in order to do that, we're going to use the equation by Max Planck, and which is E equals hf. So we just take the energy that's required, right? It goes from -5 to -1/2, so that's a difference of 4.5. So it has to have 4.5 EVs. That we're going to plug that in for E, and we just solve for the frequency. However, there's a bit of a problem, right? Because if we use this constant here, this is in joules. So we've got to first convert EVs into joules, then we can use this and find this frequency. If we don't want to do the conversion, we could just use this number instead, and then we're all done. So I'm just going to show you both processes real fast, right? So if I have 4.5 EVs and I want to convert, again, I use the charge, elementary charge, that number. So I multiply 4.5 by the elementary charge here, 4.5 by elementary charge, and I get 7.2 times 10 to the -19th joules. That's the answer, or that's the amount of energy in joules. I can now plug this number in for E, okay, and rearrange my equation, and I can plug it in, chug, right, and I get a frequency of 1.09 times 10 to the 15th hertz. Or if I don't want to do the conversion, make my life a little bit simpler, I just take E in its current form, 4.5 EVs, and plug that straight into the equation and use this other constant instead, right? Plug it in, do your math, comes out the same number. All right? Okay, then once the electron is at a higher energy level, okay, then it will eventually fall back down to the ground state, but it can do it in different ways. It can either just fall straight back down and then re-emit a photon with the exact same energy level that it was absorbed, so it would emit a photon with 4.5 EVs of energy and with the same frequency as we just calculated. Or it could fall right by starting up at the third, and then it'll fall to the second, right, and then fall to the ground state, and then actually emit 2 energy or photons in the process. It could fall step by step, third to second to first, to ground, and then emit 3, right? It could do it in any combination. It's kind of random what it will do. Now, there might be more probable one than the other, but we don't have to worry about any of that. Okay, so let's say that in this particular case, it started from the third and then dropped down to the second, and then from the second down to ground. And we want to find out the frequency of the photons emitted in both of these cases. So we just do just what we just did before, right? So we take from the ground or the third state down to the second state, should have an energy level of 1/2 EVs or electron volts of energy. Then it drops from the second, or sorry, then we want to calculate that frequency. So we take that 1/2 EV, we plug it into our equation, right? We're going to just solve and we get our answer. Then we're going to do the same except for the other one, right? So we go from the second one down to the ground state. So that's a difference of 4 EVs. So the energy will be 4 EVs. What photon has the energy of that? Plug it into our equation, figure it out, and here's our answer. Okay, so the things that you need to know is just these general concepts of how to calculate it, but each atom has its own different energy levels depending on the number of protons, number of neutrons, etc. Okay, there are different series, and people are looked at different for all the different atoms and all these different energy levels and figured all this stuff out. We don't need to know how to figure out the amounts of energies. We just need to know how to figure out, given the levels of energies, what are the frequencies or the energy levels of those photons coming off, okay? So the other thing that you need to know is, as a result of this, because each type of element or each atom type has a different series or different amounts of energy levels, you can only get certain colors from different so you can only get certain colors from different types of atoms. So for example, up here we have this top graph is a spectrum of hydrogen gas, okay? And so you can see that it will emit this wavelength, whatever that is, 400 and something, this wavelength that's bluish, this wavelength that's greenish, and this one that is red. Those are all the possible energy levels that a hydrogen atom can emit. Those are all the possible energies of those photons. However, mercury has a lot of different energy levels, right? and a lot more. Okay, and you can look at any gas that is excited and giving off light, and you can look at it through a spectrometer, and it would separate these different bands, and you can figure out what those, you can actually identify different materials by according to which colors you see. Okay. All right, so now we're finally into what we want to talk about today, which is simply nuclear radioactive decay. Okay. So a couple of quick things is a lot of this is going to be review. For example, proton, you know what a proton is, right? I'm not going to really talk about most of these things. I already know you know it. So proton, you know what that is. A neutron, you know what that is. A nucleon, you may not remember what that is. So a nucleon is simply a particle in the nucleus, found in the nucleus. So that actually includes two types of particles, right? Protons and neutrons are both nucleons because they're both found in the nucleus. So nucleon is a more general term. It includes neutrons and protons. Okay, electron is, well, you know what that is. An electron cloud is a probability density of where the electrons might be found at any given time. All right, other things you should be aware of, right? You should be able to look at things like this, symbols like these, and be able to tell me what isotopes these are. So this one right here is carbon-12. This one over here, can you guess what it is? You should be able to guess, and it is iron-56. Okay, so these are the isotopes names. How do we label these isotopes? Okay, so the 12 represents something, the 6 represents something, and this is the symbol, obviously, for carbon or whatever your element is. So what we do is we have 3 different numbers that you need to be very familiar with. This is all chemistry, so you should know it. You can skip this slide if you already know it. Z is the symbol we use or variable we use for the atomic number. The atomic number is the number of protons. A is the symbol we use for the number of nucleons. Again, that means the number of particles in the nucleus. So number of nucleons includes protons and neutrons. And then N is the number of neutrons. Okay, so 12. What do you think 12 represents? Okay, is it the atomic number, a number of nucleons or number of neutrons? 12 should be the number of nucleons. 6 is the atomic number or number of protons. Okay, so this is how we represent our symbol or any isotope. We always give the symbol that is shown in the periodic table, sorry, and then we put on top, we put the number of nucleons, on the bottom we put the number of protons. If you want to find the number of neutrons, you just simply subtract the two. All right, so what happens when you add, just a quick check, what happens when you add a proton to an iron-56 atom, right? So if you add a proton, that means the number of protons on the bottom, or the atomic number, goes up, right? Also, the number on top goes up because you have more nucleons as well. So now it becomes something. What element is this, though? Has the element changed? And it has, because elements are determined by the number of protons. It is now cobalt. Well, that should say 57. I'm sorry. This is now cobalt-57. All right, and then what happens if you add a neutron? Well, the number on bottom does not change because it's still the same number of protons, but the number of nucleons goes up from 56 to 57. Okay, what is this an example of? This is, what isotope is this? This is the isotope of still iron, but it's iron-57. So again, the element only changes if you change the number of protons, which I'm sure you guys already knew that. So these are both iron, but these are different. These are examples of different isotopes. Okay, so what is an isotope? An isotope, isotopes are evidence that there's an existence of neutrons, right? If you can have two atoms that are the same element, but one is slightly heavier than the other one, there must be something else there. There's not more protons because it's the same element, so there must be something else there, and that was our evidence that there must be something else, and we figured out that we called those things neutrons, right? And they're neutrally charged. So two isotopes will be the same element, but different amounts of neutrons. Isotopes can exert slightly different properties, okay? And also, it is most noticeable that the difference between isotopes is their atomic stability, which is what we're going to talk about next. So the main difference is that some isotopes are stable while other ones are not. All right, so what actually keeps a nucleus together? What makes it stable? Okay, something has to be pulling it inwards, those nucleuses, all the particles in the nucleus, because the nucleus is made of a bunch of protons. Protons are all positive, and positive charges repel. All those protons are trying to push away from each other. So what's keeping it together? Something must be. There must be a greater force pulling inwards, and that force that's pulling inwards, okay, inside here, that's pulling inwards must be, or is what we call the nuclear force, or strong nuclear force. The strong nuclear force, so you know, in general, is much, much, much stronger than the electric force. That's why it's able to keep it in, but it also has a much shorter range. So once you separate them a little bit, then the strong nuclear force isn't going to keep them together. Stability is an observed phenomena, and stable atoms, we call them, unstable atoms, we call them radioactive. So we're going to talk about now radioactive decay. So we're now going to talk about radioactive decay. So when an atom is unstable, the nucleus, when the nucleus is unstable, it will emit something out. Okay, there's different types of radiations. Do you know them all? There are three main ones that you need to know. They include alpha decay, beta decay, and gamma decay. Okay, so let's go over the three types. An alpha decay is simply, an alpha particle is simply a helium-4 nucleus. That means it has 2 protons and 2 neutrons. A beta decay is an electron that is shot out from the nucleus, which is strange since there are none there. And a gamma decay is simply when energy is lost. All the particles stay there, but you lose energy in the form of an electromagnetic wave. Remember, gamma ray is actually part of our electromagnetic spectrum. So you'll notice it has a very high frequency, and that means it has a very short wavelength, but also it means it has a very high energy. Because remember, E equals HF. So the bigger the frequency, the bigger the energy. So these are very, very high energetic electromagnetic waves. All right, so a couple of things you need to know when we're writing things down. You should know the symbols for neutrons, protons, electrons, alpha particles, gamma rays, and beta particles. So the symbol for neutron is a lowercase n, and then it should be 1 on top because it is a nucleon, and 0 because it's not a proton on the bottom. Okay, proton would be 1 and 1, 1 because it is a nucleon, and 1 because it is also a proton. So it's 1 and 1, and the symbol is P. Electron would be E. The top number would be 0, right, because it has no nucleons. Electron's not in the nucleus. But on the bottom number shouldn't be 1. It should be -1 because it isn't necessarily a proton, but it has the opposite charge of a proton. An alpha particle, like we said, is a helium nucleus, so the symbol is He for helium. And that means it has 2 protons, so the number on the bottom is 2, and 2 neutrons. That gives you a total of 4 nucleons, 2 protons and 2 neutrons. Gamma rays are the symbol gamma, and there's 0 and 0. And beta particles are, again, an electron, so it's the same as for a beta particle. Okay, now that we know the symbols, then we have some different equations or different reactions that we could have. During any reaction with nucleuses, you always just need to make sure that you balance your nuclear equation. So for example, uranium-238 on one side, right over here, needs to have the same number of numbers on the top and on the bottom. So it has to have the same number of protons and the same number of nucleons on top. So same number of protons and nucleons. So if it does an alpha decay here, it's performing an alpha decay because an alpha particle or helium nucleus is shooting off, then we say, okay, what is the resulting element here or isotope that we're missing? So in order to balance this equation, we started with 92 protons. Helium has 2, so this one must have 90. So if we look on our periodic table, I'm going off of memory, I think it's thorium, some TH something. Okay, on the top we have, so we start with 238 with uranium. Helium has 4 nucleons, so on the top it'll be 234. So the answer is I don't know what the TH is, but 234, TH, 234. Okay, so that is the balanced equation. Okay, you just got to always make sure that numbers on top balance and the numbers on bottom balance. All right, then we have several examples of other examples of decays. We have an example here of an alpha decay like we just did. Notice the alpha decay, your number of protons or your atomic number goes down on the periodic table, goes down by 2. Okay, you can also have a beta decay where instead of going down on the periodic table, your atomic number actually goes up. And what happens is you have an electron shoot off, which is strange because there are no electrons inside the nucleus, right? So what instead happens is you have a neutron, one of your neutral particles inside the nucleus, decays into a proton, positively charged, and an electron, negatively charged. Okay, so a neutron splits into a proton, which stays in the nucleus, so therefore the total number of particles in the nucleus is the same, the total number of nucleons, 234 in the beginning, 234 at the end. So the neutron turns into a proton, which stays behind, and an electron, which shoots off. Okay, so while the number of nucleons stays the same, the number of protons goes up, because you're turning a neutral particle that was a neutron into a proton. You got one extra proton. All right, and then the last one is a gamma decay, which often usually happens in corresponding to other types of decays, but the gamma is just a photon or extra energy that is also released in the form of electromagnetic radiation, or a gamma particle or photon. All right, so let's just practice balancing some of these equations. Take a minute, try it, and then check your answer. If you want, you can pause or keep on going. Okay, so in this one we have oxygen 15, and it balances, or we're trying to figure out what the type of, or the missing particle or element is, isotope is. This obviously undergoes a beta decay. So the ending result should be the total number of nucleons stays the same, right? This is 15, over here should be 15, 0, and this should be 15, right? 0 plus 15 is 15. And then on the bottom, the total on the bottom should be the same. It starts off as 8. This is -1, so that means this needs to go up to be 9. 9 plus -1 is 8. So the answer is whatever 9 is. Apparently it looks like nitrogen 15 is the answer. Okay, on the bottom one down here, we're going to do the same thing, except we're missing the thing in the beginning, right over here. So we say lithium on this side has 3 protons, helium, apparently this is an alpha decay. Helium has 2, so the total is 5. This has 0, so this one should have 5, okay, on the bottom. On the top, we've got 7 here, 4 here, total is 11. On this side, we already have 1, so we only need 10 more. So it should be 5 and 10. That makes it boron, I think it's boron, boron 10. So notice this is boron undergoing an alpha decay, but it is what we call an induced reaction. It didn't decay on its own. For example, oxygen decayed on its own. It just underwent its own. It was just sitting there, and it just decayed into nitrogen with a beta decay. This one, though, you had to make it decay by shooting a neutron at it. It's called a forced reaction. So we can have a series of decays, and oftentimes we can have a radioactive chart. Okay, one radioactive element, one radioactive isotope that's unstable might decay into something else that's also unstable, which also decays, which also decays, which also decays again. And so it can decay again and again and again. Sometimes you even have an option. Sometimes there's no option. Uranium-235 always turns into the same thing. Okay. However, some items, this one, for example, could undergo alpha or beta decay. You never know which one it will do. It's totally random. And so it'll either do one or the other. And then eventually, though, it'll end up being the same thing. So either just does alpha beta, or sorry, beta alpha, or it could do alpha beta. In the end, though, it'll end up the same item, and it'll keep on going until eventually it is apparently lead 270 or 207 and is finally stable. So you could try and fill out this chart, and that would be really good practice. Okay, on the next slide, we can try that together. So here is a piece of the chart that we just saw, the part that I noted out where it can change in different ways. So you can try these different decays. You can pause it and check your answers. Okay, if it does beta decay, what will it become? If it does an alpha decay, what will it become? And check each one. The answers, if you've already tested yourself, are as follows. Moving on. Okay, when will one of these atoms decay? How do you know when an atom will decay? Is it possible to predict when an atom will decay? The actual answer is no. A lot of people think there is because of a thing known as half-life. But that doesn't mean that half-life doesn't tell you exactly when a particular atom will decay. It only tells you the amount of time it takes for half of the atoms to decay. You never know which atom will decay. So decaying is radioactive decaying is 100% random. You never know when a single atom will decay. Even though as a large chunk of material, you can figure out when half of it will decay, you still never, if you just pick one of those atoms, you'll never be able to know for sure when it'll decay. It could decay right away, or it could take eons and eons and eons. Even when you get down to the last particle, it may never decay, right? It could take forever, or it could just take a really long time, or it could still go relatively fast. So how long it takes for it to decay has something to do with what we call half-life, which you probably already know about. Okay, and half-life is simply the time it takes for the material to decay half as much. So if we had, for example, a whole kilogram of uranium-238, okay, and it was going to undergo, I can't remember, an alpha decay and become thorium-234 or whatever that was, and it becomes something else, right? After whatever the half-life is, if it's 13,000 years, right, it means it would take 13,000 years for half of that uranium to become thorium. And then you have now 50% uranium and 50% thorium. Then another 13,000 years or whatever that is, later it will become a quarter of the original amount is still uranium, and the other part is thorium, or you know what, even some of that thorium could have decayed into something else. Okay, so it will decrease at a rate, and it gets asymptotically closer to the x-axis. Here's a typical half-life graph. One of the questions you could have is just have a graph and then just figure out the half-life. Go ahead and try it. Okay, if you've tried it, you can see that we look at the first value, or the maximum value, and it looks like we have about 32,000 looks like grams here. Atomic mass is in grams, so 32,000 grams of substance. That means half of that will be, what, 16,000 grams? So half of that will be right about here at 16,000 grams. And then we just look and see how much time it took, going over how much time it would take to get to half of the original amount. And it looks like, drawing a line down, it's about 16 days, because that's the unit of whatever this substance is. Here's a typical half-life question. You can have the half-life, let's say, of radium is 16,200 years. If there is 36 grams of radium, radium-226, now how many grams will there be after 4,860 years from now? So in order to figure out a problem like this, you've got to just break it down and just think about the problem and just solve. It's just mostly just thinking about it. For example, I know that the total time divided by the number of half-lives will equal the number of, the total time divided by the half-life gives you how many half-lives have occurred, okay? So for example, the total amount of time we can see is about 48,000 divided by 16,000, and you find out that 3 half-lives have occurred. Or in other words, it is split in half 3 different times. So we can say, all right, so then we take the original amount, 36 grams, we split it in half, we get 18. That's how much there's left after 16,000 years. Okay? After another 16,000 years or so, there is half of 18 again, so there's only 9 grams left. After another 16,000 years, there's half of 9, so there's only 4.5 grams. That's a total of 48,000 years later. So that means that the answer will be there. Here's another example of a half-life question. It's just my made-up stupid example. Okay, at the beginning of the period, let's say there is 32 students of attention minium. I'm just making this up. 1707, which is my room number. What is the half-life of attention minium 1707 if there is only 2 students at the end of the period? Okay, so if we were going to solve this, we would think about this, and instead of knowing the half-life, we've got to figure out the half-life. So first things first, we've got to figure out how many half-lives have actually occurred. So if we start with 32, after one half-life, whatever that is, we don't know what that is, after one half-life of time, we would split our number of students in half. So we go from 32 down to 16 students left. After another half-life, we get down to 8. After another half-life, down to 4. And after the final half-life, we get down to 2. Okay? So that means there has been 1, 2, 3, 4 half-lives that have occurred. So if there's been 4 half-lives, again, I know the total amount of time divided by the half-life should be the number of half-lives that have occurred. I could rearrange this, right? Take this number, multiply by half-life, bring it up here, take this number of half-lives, divide by both sides, get it get over there. And I will then take the total time, divide by the number of half-lives, and it'll tell me how long a single half-life is. A typical period is 50 minutes long. So if we have a 50-minute long period and 4 half-lives have occurred, then that means each half-life is only 12.5 minutes. Another typical problem. And you just mostly have to think about it and just do the algebra. Okay, what are some uses of radiation? We're pretty much all done here. We just got to wrap things up. What are the uses of radiation? There are lots of different uses. Most of them sound pretty evil. For example, the first one is creating mutations. Might be fun, but maybe a little evil too sounding. So creating mutations is actually really important for us, especially with this idea of evolution. Okay, when creatures are bombarded with radiation, their bodies will have to mutate to adapt. So there's radiation around us all the time, and we're used to it. Our bodies are used to it. Okay, there's what we call background radiation. They're low dosage, but there's radiation all around us. And this radiation actually allows us, when we procreate, to create mutation after mutation, and slowly we adapt ourselves to our environment, and it allows us to change our genes and create a better version of ourselves, right? Okay, other examples is killing stuff. You can kill stuff with radiation. Again, that sounds bad, but we're talking about killing bad things as well, like bacteria. They use it for food. It's called irradiated beef. I don't know if you've ever heard of that, but they have irradiated beef where they're just shining ultraviolet light on the beef and it kills the bacteria. It's a type of radiation. It's electromagnetic radiation, right? Or they also irradiate mail sometimes to kill germs and things like that. Tumors, they use radiation, right, to also kill tumor. They get that high gamma rays, those high gamma particles or photons, and they use that because it has lots of energy, and they send it in and they try and kill the tumor before the tumor kills the patient. Gambling, again, remember, it's 100% random. So they have made 100% random number generators at gambling casinos to help keep things actually truly random. Smoke detectors. Smoke detectors have a little bit of americesium. I can't remember the number, but americesium, I think 270 something. And what it does is it has the americesium or the radioactive material here, and then over here they have a detector. And as the americesium decays, it sends alpha particles over to the detector, and it hits the detector, and the detector says, "Oh, it's there." And then another sends another one and another one and another one. And as long as the detector keeps on receiving alpha particles, it's happy. As soon as smoke drifts up and gets in the way, right, the alpha particle will hit the smoke particle instead and won't get across to the detector. And as soon as the detector doesn't sense any more alpha particles, it starts complaining, wah, 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 right? And it complains, and then you know, hey, there must be smoke. That's how a smoke detector works. Okay, also, you can use radioactive dating. Things naturally decay at a specific rate. Carbon specifically also decays, not carbon-12. Carbon-12 is stable, but there's another kind of carbon. I can't remember which one. One of the carbons also decay, and so depending on how much of that carbon is left, you can actually figure out how old it is using your half-life. And of course, our most important evil version of our uses of radiation would be, of course, atomic bombs, right? Which is what we are going to be talking more about. We actually will talk more about atomic bombs, but for the most part, we just need to talk more about what we call an induced nuclear reaction, which is what splitting an atom is all about. We'll talk about how you can release energy in multiple ways. One, if you want to blow something up, right? How do you make an atomic bomb for that? And also, two, if you want to release that energy not for killing people or things, but to instead harvest energy and actually get electricity out of it like we do in nuclear reactors. All right, guys, that is it. I will see you next time.